Hello everyone. I updated my OBS settings here, my Open Broadcaster software, and figured out how to make a scene with more than one element, and I was able to add in my laptop camera so you can see me while we're going through the lecture. One thing to point out, my camera is up here and my tablet is down here in front of my laptop, so it's going to look a lot like I'm not looking at you. But that's just where my tablet needs to be for me to proceed. Okay, so today we're going to start talking about dictionaries and hash tables, and this topic is going to be important to us for the Project 3. And I've seen people have already started working on it and already started looking at the unordered map, and we're going to do some examples today, and we'll also talk a little bit more about the unordered map and how it relates to Project 3. Okay, so the idea that we want to look at today is this idea of a dictionary abstract data type. And what we really want to talk about is how to look up data using a key. And until now, generally our key that we used to look things up was an index. And that works really well in a lot of situations. In fact, we're going to continue to use that in Project 3 for some purposes. But there's other times that we want to use, say, a different type of key than an unsigned integer in the range 0 to n. So we're going to look at this, what's called a bucket-based data structure, where there's more than one thing that goes in it. There's the key and the value that goes with the key. We're going to talk today about hashing functions, how to turn something into a hash index, into our hash table, and next time we're going to look at collision resolution. So we're going to mention collision resolution a few times today, but it's going to be primarily our topic next time. Now, the idea here is that we want to have some sort of key value pairs that we can put in. And we use this idea of a dictionary for two reasons. One is that it's a way to talk about using something like a string as our key rather than an integer. And also it's very obvious why we want a value associated with the key. So the key might be a word, the value associated with it might be its pronunciation, definition, etymology, etc. Now we've got to have two operations to make a container, any container, useful. We've got to be able to put things into it, and we've got to be able to look at the things that are in there. So we've got to be able to insert new items, and we need a way with this key value based data structure to say, hey, here's a key, please show me the value associated with that key. So we're going to have operations where we check if something is in the set. Sometimes we just want to know, is this in there or not? Other times we want to look up the value associated with it. And we want these operations to be efficient. We want insertion, searching, and it's going to be a side effect that remove is going to be very efficient also. It's not absolutely crucial, but it's really important in a lot of implementations and uses, I shouldn't say implementations, a lot of uses of this data structure. A very fast removal would be very useful a lot of the time. So we want to make those three operations as efficient as possible. Things that are going to be inefficient are things we're willing to give up to make those operations faster. So sorting the dictionary is out, which is where our analogy to a dictionary sort of breaks down a little bit, is usually when we use a physical dictionary, we want it to be in alphabetical order. But in an electronic dictionary, we might be willing to give up that alphabetical order to get that fast lookup. Other things that we're going to give up that are going to be inefficient is selecting the kth largest item in a dictionary. In fact, we're not going to be able to do it at all. So if I want to say, hey, tell me the 10th word from the end of the dictionary or the 20th word from the beginning, There's going to be no easy way to do that. Joining them is going to be inefficient, and that would be somewhat inefficient no matter what we did. It's not going to be any more inefficient than it has to be, but it's not one of the things we're optimized for. And we're also going to have a lot of other basic operations for a container data structure. Things like a constructor. If we've got a constructor, we probably need a destructor. Testing, is the container empty? What is the size? How many things are in the container? Copy constructor, etc. So basic operations, yeah, we'll have those also. So if we wanted to do this key value pairs and looking things up, we don't need a hash table to do it. We could do it other ways. So we could say, hey, let's make it sorted. Let's always keep the keys in sorted order in there, and you've done a implementation of a sorted priority queue. We could create a sorted dictionary. The problem with the sorted dictionary is insertion would be O of n, because we've got to find where it should be. That's binary search is log n, but then to make everyone else move over to make room for the new element, that's going to be O of n. If we kept it unsorted, well then it's easy. We just add a new word to the end of the dictionary. But then when you want to say, is word X in the dictionary, we've got to look at every word because it's unordered. So now insertion is fast, searching is slow. All right, what if we did it with linked lists instead of vectors? Well, with linked lists, searching is always O of n. Even if it's sorted, searching is inefficient because there's no way in a linked list to go to the middle in O of 1 time. If we want to go to the middle, it takes us O of n time to skip over the first n over 2 items to get to the middle. So we can't do binary searching on a linked list. Okay, how about binary trees? Now we're a little bit out of order here because it would have been a little bit better to do binary trees first and hash tables after that, but the hash tables are more important to us for the project. So we didn't want to leave them as this sort of magical black box. We want to get into the details about hash tables work quickly after the midterm so we can have it for project 3. So if we used a binary search tree, then we would get an average case log n, a binary search in the binary tree, but we could get worst case. The worst case happens when we get a big stick. If we insert them in a bad order, we could end up with a big stick and then we don't get log n behavior anymore. Now we can fix that, and in fact, I should have put it in bold here. The map data structure from the STL does give us not just average case log n, but the map data structure gives us worst case O of log n. And that's something we're going to look at how to do it. So how could we make a binary search tree have worst case log n? We make sure it never becomes a stick. And we're going to look at one of the 2 most common ways to do that. So when we look at binary trees, we're going to start with binary trees. Well, actually, we're going to start with trees in general, binary trees, binary search trees, and then we're going to do what's called AVL trees, which is a self-balancing binary tree. It makes sure you never get too stick-like. The STL map doesn't actually use AVL trees. It uses what are called red-black trees. Now, we do usually like to stay consistent with the STL. The reason that we're not going to teach you red-black trees is the AVL trees that I can do in 30 slides, red-black trees would take over 100. And they accomplish the same thing. They make sure that the tree never becomes too stick-like. They want to make sure that you get a worst case log n. The red-black tree is used by the STL because it's a little more efficient but it's harder to understand. It's much harder to prove that it will never be too stick-like. And so we're going to go with the one that's more reasonable in terms of teaching it and understanding it. So we're going to teach you AVL trees, but red-black trees accomplish the same thing in a slightly more complicated way. Okay, so if we did that, we could get a worst-case log n. That would be pretty good. But the hash tables, which is what's used by unordered map in the STL, we are going to get an average case of O of 1. And that's going to be really useful to us. And it does have a worst case of O of n. That's hard to overcome. It's doable in some implementations of a hash table. We could get a worst case better than O of n, but what we'd rather concentrate on is not getting that worst case very often. So we're going to look at ways to build a hash table and ways to do the collision resolution, which is going to give us the that worst case idea and how to analyze it. So if our number of keys is small, then we don't need hash tables. If I've got something like birthdays, the day and month of a birthday, if all I care about is putting people in order or looking people up and saying, hey, who's got a birthday today? Okay, so I take June 1st, I translate it into an integer. It's going to be around 150 some. I'm not going to do the math in my head. So, we're going to go January 1st is 0. It's at index 0. Therefore, February 1st would be at index 31, etc. So today would be around index 150 something, like 152-ish or somewhere around there. So then we could look at index 152 and see what's there. So when we've got these small number of fixed keys, things get easier. But what if we don't? What if we don't have that really easy case? Well, we can always do direct addressing. This is what we do when we have those very small values. So, for example here, suppose I've decided U of M is great, but there's just a few things I'd like to do that I can't do here. I'm going to create the University of Dave. And at University of Dave, we have people who get in on the ground floor. You can have a one-digit student number. And although I might not have 10 students to begin with, I could make my student record table of, it looks like size 10 here. So I can make my student record table size 10. The first 10 students are going to get single-digit student numbers, and I can just use your student number to directly address your data. I say, oh, student number 2, hello, student number 2. I go to index 2 in the table. There's your data. Easy to look that up. And when we have 5 students, this gets really easy. But what if we have 50,000 students and we don't want to make student ID numbers easily guessable? If everybody has a one-digit student ID, it's pretty easy to guess that his ID might be 4, because I don't know anybody that's 4. It's not me. His might be 4. And so I know his name because he's in class and he told me his name. So now I could break into student records because I know his name and his new student number. So what if we had a much larger group of possible values? Let's say I had an 8-digit student number, and even though I only have 5 students at the moment, or 6 students, even though I only have 5 or 6 students at the moment, I might have 8-digit student numbers, so it's very hard to guess somebody else's student number. So I still don't want to make a table of size 8-digit numbers. That would be like in the 100 million range. So because I have an 8-digit student number, I can't make a table that's necessarily 100 million large and have all of our student data in there as well, because all that student data may take up like a couple kilobytes, and now I'm up into the multiple gigabytes array size, and that's not going to work. So since I can't make a multi-gigabyte array, then what I'd like to do is I'd like to make the table smaller. I might still make the table size 10, for instance. Now what we're going to do here in this example is we're going to use the table size is M. So M is the table size, and so my indices into that table are in the range of 0 to M, inclusive, exclusive. So that's my indices, but what if my keys are not integers in the range 0 to M? What if my keys are strings like names? Well, what I need is this H, this hashing function. So I take key 1, I take, let's say Lucy Lou. Think of an actress name. That was from our sorting the celebrities with a stable sort. I've got Lucy Lou. I want to hash her name. What I want to do is I want to turn it into a number. I want to say, let's take that name, let's turn it into a number, and the hashing function of key 1 says she's going to be at index 0, 1, 2. She's going to be at index 2. So key 1 goes to index 2. That's what the hashing function tells me, is how to turn that string into a valid index into my hash table. So then I take key 4, I hash key 4, it tells me that should be at index 3. I hash key 2. I hash key 2, it tells me it should be at index 0, 1, 2, 3, 5. It says you should be at index 5, so I put key 2 at index 5. I do key 3. Key 3, it says key 3 should be at index 7, it looks like. And then I do key 5. I hash key 5, and it tells me you should be at index 5. But then there's somebody else is already here. When I try to put key 5 there, I've got a problem. That's a collision. And we're not going to talk today about how to deal with it. We're just going to look at how it can happen. We'll look at how to deal with it later on. Now, what it says at the bottom is actually related to a question that just popped up. Only actual keys map to an element of the array. So the dark gray ones, they just don't have any data in them yet. They are unused locations. So, like we said, we want to be able to locate items in a table by their key, and for different data types of keys, such as strings, we're going to use some sort of arithmetic operations to turn that key into a table index. And that's called the hash function. Now, we really need two parts of this. We need the transformation of the key into an integer, but then we have to limit that integer so that it fits within the table. So if, in this previous example, if I transform Lucy Lou into, 237,053,005, that doesn't fit in the table. So then I need to compress that large range of possible integers into a smaller range that actually fits in the table. So we've got to do a transformation, or we can also refer to it later in the slides as translation. We've got to have a translation function to turn some other type into an integer, and then we need a compression function to limit that integer to being a valid index. And like we mentioned, eventually we're going to have to deal with collisions. So today, like I said, we're going to talk about what the ideas are that are important to the making a hash table and the transformation and compression. Next time we'll talk about the collision resolution and how to deal with that. So first part, the T, or the translation. So we're going to do the translation to turn our key into an integer, and then we're going to that T of key produces a hashed integer. If I then compress that hash integer, I can get a valid index in the range 0 to m. And I do realize our slides sort of skip back and forth here between lowercase and uppercase m. So we can think of the hash function overall. The hash function is the compression of the translation of the key. We transform the key into an integer. We compress that integer into a valid index in our table. So let's look at a really simple hash function. Not a good hash function, but a simple one for an example. So if we take a char pointer. So I've got a char pointer, and I'm only going to look at the first letter of it. So that's what this says here, is return dereference of C. So C is a char pointer. If I dereference C, I get the first letter, and I'm going to subtract A from it. That tells me the distance between the first character pointed to by pointer C and the distance between that letter and A. So for example, banana comes in to the function. We dereference it, we get the letter B. The letter B minus the letter A, if you look at the ASCII table, they happen to be one position apart. Because they're one position apart, B minus A is equal to 1. We say, hey, that should go at, index 1 is what should come out of there. So that tells us we should look at the table at index 1. And if you look at the table so far, apple, A minus A is 0, apple's at index 0. The number associated with it here might be, say, how many of those fruits I have in my pantry. This is not correct at the moment. I have about 6 or 7 apples and no bananas, but the example works anyway. So the number represents, say, how many of that fruit I have on hand here in the house. So I look at apple, it's at index 0. The value 1 is associated with the key apple. The key is what gets me there. The number associated with it is what I look up. So then I say, oh, banana. There are 3 on the shelf. So that's how the hash function works. Now, what if I hash lemon? I look at L, L minus A. The distance between L and A is 11. And, oh, wait a minute, that is an invalid index. My hash table isn't that big to allow lemons to go with a simple hash function like that. So what we need now is compression. So that's the second piece of this. So we need to compress our hashed integer into a valid table index before we go looking at index 11 and getting a segfault. We don't want to do that. Okay, so lemon comes in, it goes into the hash function, 11 comes out, so the 11 that comes out of the hash function goes into the compression. The compression takes, for instance, one way to do this would be modulo the size of the table. So I take 11 modulo 8. So 11 modulo 8 gives me 3. We look at index 3. We say, we can put lemon at index 3 of the table. Now, suppose I decide to look, oops, sorry. I thought there was another slide here. So suppose I decide to look up a fruit that, say, began with D. Ooh, I'm going to have to pull out the durian example here. Not something I'm super fond of. I have had a pastry made with it. I tried to cut one open myself, and that was a very, very bad incident. So if we said, hey, let's hash durian, D minus A is a distance of 3. Durian should go at index 3. Oh, no, lemon's already there. We've got a collision. Next lecture, we'll deal with that. So let's look at what a hash function needs to do. So in order to get the benefit of a hash table, what's the benefit of a hash table? That O of 1 average case lookup. So that's our benefit that we want. To get that benefit, we need a good hash function. Now, we've got a few requirements, what a hash function must do, and then we've got what it should do to be considered good. So what it must do is it's got to be easy to compute. If taking a string and turning it into an integer takes like O of n cubed time, that's terrible. That's a terrible hash function because it's so slow that I won't get the benefit at all, ever. It's impossible to get that benefit. So we've got to have something that's easy to compute, and it has to compute the same, and also other things. So besides being easy to compute, it has to be able to compute a hash for every key. I don't want a function that I give it banana and it segfaults. So it's got to be able to take any key of the type that I'm trying to hash. So if I write a hash function for strings, it has to be able to turn any string into an integer. It can't say, oh, banana's a segfault. The other thing it has to do is it has to always compute the same hash for the same key. So if I hash banana and it says 1, and then later on, and so I put banana at index 1, and then later on I say, hey, let's look up banana. And this time it says 12. I go look at index 12 and there's no banana there. I go, oh, banana's not in the hash table. So it's got to be, there's a name for this. Sorry, that's a big long word. I'm not going to say it while I'm typing it out. Deterministic. Deterministic means the behavior is predictable, the behavior is consistent. So we've got to have a hash function that's easy to compute. It's got to compute the hash for every key of the type that it's defined for, and it's got to give the same hash for the same key every time. Now, the good thing, to get a good hash function and to get the complexity average case O of 1, we need to distribute the keys evenly. If we distribute them evenly, it will reduce the collisions. It'll minimize them. We're not going to be able to prevent collisions, but we want to reduce how often they happen. So, for example, here, we've got a hash function that says, oh, you want to hash this key? Return 0. Now that one meets all of our musts. It's easy to compute. It computes a hash for every key because it doesn't even look at the key. It computes the same hash every time for the same key. Well, more than that, it computes the same hash for every key. So this one is terrible because this one maximizes the collisions. It's saying, everybody go to index 0. So the first key that we hash goes to index 0. Everything after that is a collision. Every other different key is a collision. And so that's a terrible hash function. It meets our musts, but it's terrible at the should part. It is not a good hash function. Okay, so for example here, if we have our table here, and I don't even have to pull out a really obscure fruit like durian, if I pull out orange, O minus A is 14, 14 modulo 8 is 6, orange should go at the same location that grape is, and I get a collision. Now let's just say here, for example, I would like to resolve this. What's a way that I could resolve this? And this example works slightly less well in our 30-second delay video. But what could we do here? I'm going to pause, let you think about it. I'm going to give you the answer rather than waiting for everyone to respond. But we could say, hey, let's go to the next index. Oh, wait, well, the next index, that one's used also. I could go to the next index. Wait, I don't want to go off the end of the table. Oh, we could wrap around using modulo. I could increment and modulo. I could wrap around to the beginning. Oh, that's a collision. That's a collision. aha, I found an empty place in the table. It took me a while to get there, but I found it. So that's one of the collision resolution methods we're going to look at next time. So that what we just did is called linear probing. Because we use the hash function to say start here, and then we start a linear search from that point on. So that's just sort of a preview, just so we know what might happen. Okay, so I've got a hash table of size m, and we want to make m on the order of the number of items expected. Now, we do want to guess a little bit high because if I'm even off by 1, I don't want to have it exactly full. If I'm off by 1, then I have to grow the table just to put one more in. So we might go a little bit high, and that's similar to our example earlier. Remember our example earlier, we had a hash table of like size 8 or so, but we only had 4 or 5 students in it. So we made it a little bit bigger than we needed to. And we'll look at next time, when we look at collision resolution, we're going to look at what we should do about making it a little bit bigger than it needs to be and how much bigger it should be to be reasonable performance, etc. So we've got to have a hash function transform our keys into this range. We've got to do the translation step. We've got to do the compression step. Okay, let's look at an example. Before we get to the more complicated one, strings, let's look at a slightly easier one, floating point numbers. Now, floating point numbers is actually hard if we allow unlimited range. If we limit the range, let's say I limit the range to numbers in floating point numbers, doubles, say, in the range of 0 to 1. Well, then the translation is pretty easy. I just take your key and I multiply it by m. So let's say, for instance, let's say I had a key. My key was equal to 0.5 and m was equal to, let's say, 8. Well, I multiply 0.5 times 8. That gives me 4. I take the floor of that and say, hey, 0.5, you should be at index 4. And the reason I did the floor there is, what if I didn't have a number like 8? What if I had a number like, say, 9? 0.5 times 9 is 4.5. I can't put it at index 4.5, so I take the floor of that and say, oh, if the size was 9, you would still go at index 4. Okay, well, what if I know that my double values won't be in the range 0 to 1, but there'll be some range s to t. So s and t are 2 double values. So what I can do is, if I take the key you give me minus s and divide by t minus s, this right here produces the range 0 to 1. Now that I have the range 0 to 1, I do what I did before. I multiply by m, and I take the floor of that. Now we've got an example here. It says, okay, try this. We've got a range, we've got an m, we've got an h, so we have to figure this out. Okay, so I've got, according to my formula there, I'm going to get rid of my markings. So according to my formula, I've got the key, which is 3.65 minus 1.38 divide by 6.75 minus 1.38. I calculate that, I multiply by 13, I take the floor of that. Okay, we can simplify this one a little bit. That's 2.27 divided by, let's see, we've got a 5.37. Okay, take that, multiply by 13, take the floor, and now I'm beyond the range of my doing quick math in the head. this is going to come out to be around, so this is going to be approximately 5.95, which when we take the floor says you should go to index 5. So I had a note in the margin here. So going back through that, that's our formula. We plug our values in, 5.495, take the floor of that. We say you should be at index 5 of the table. Okay, what about integers? Well, integers are pretty easy. My translation just says, oh, the translation of this integer is the original integer. That was easy. Now I just have to compress it. And let's look at compressing. Compressing it, simplest one is to use the remainder upon division. Very easy, very straightforward. There's a slight problem here in that if the keys are randomly distributed, this works great. If the keys are randomly distributed and every possible integer is equally likely, this works fine. However, what if it's not randomly distributed? What if I'm currently have a table size of 10 and I let people pick their own numbers? I might find 5s and 10s because, hey, we use base 10 number system. If I had people from a different culture, maybe 7 is a very lucky number, and some people might want to pick 7 or 8. So I might end up with very few 2s or 1s. I might end up with lots of certain values like 5s and 7s. So if we let people pick them, it might not come out random. If I was, say, trying to do midterm multiple choice section scores, they're all multiples of 2.5. So if I have a bad M would be where M and keys have common factors. So how can I reduce the chances of that? Well, one way it would be to pick a better M, make my table size something like in the last one. Why did I choose 13 as a table size? Because it's a prime number. Prime numbers reduce my chances of getting these sharing common factors. So one way to do it would be to pick a table size that's a prime. Now, what if I have to grow my table size? That becomes a little bit more problematic to grow my table size because my new M, to be a good M, would also have to be a prime. Then I have to go find a new prime that's bigger than my old one, which takes a little bit of time. It also, as we get a bigger and bigger table size, the prime numbers tend to be further and further apart sometimes. Sometimes they'll cluster tightly together, and sometimes they'll be far apart. And so that wouldn't produce necessarily a good growth of my table. So, I'm slight misremembering on our order here. So we'll come back to that idea of the controlling the table size and what to do about that modulo. What about strings? What about if I take strings and I say, hey, let's take the ASCII values. Let's turn each letter into a number. That's easy. And then we take those numbers and add them all up. The problem is I just gave you 4 words that all of the sums of the ASCII values all become the same sum because they're just the same letters in a different arrangement. Even if I don't have the same letters in a different arrangement, if I had the words like AD and BC, those would have the same sum even though they have completely different letters in each of those 2 strings. So summing up just the ASCII values is not a good hash function because there's going to be a lot of collisions there. And also, here's another rule of thumb. If you can make collisions this easily, it's not a good hash function. If it's that easy to make them up, it's not good. So what we can do is we can still go with this idea of using the ASCII value of each letter, but we're going to add something. Position is important. See, if I had the numbers like 1, 2, 3, and 3, 2, 1, they would go to different positions as integers. So 1, 2, 3, and 3, 2, 1 would go to different positions because the digits have a meaning. Each digit has a different meaning. If I said, hey, I want to hash integers, let's hash integers by summing up the digits. Well, then 1, 2, 3 goes to index 6, and 3, 2, 1 goes to index 6, 2, 2, 2 goes to index 6, 0, 4, 2 goes to index 6. All these go to index 6. But if we leave the position being important, then all of these values go to different locations. So, just like with integers where position is important, we're going to do the same with letters. Now we can break down this number 1, 2, 3 into its component parts. It's 1 times 10 squared plus 2 times 10 to the first plus 3 times 10 to the 0. If I knew up front that it was going to be 3 digits long, these powers are easy to predict. What if I didn't know how long the number was going to be? What if I just read a number into memory? Like, what if I was writing Cn? What if I was writing Cn goes into the integer I? Let's look at what we could do, because this is going to make the next slide a little bit easier to understand. So right now, I say, okay, to do my Cn, I'm going to keep my running total of my sum. Right now, my sum, let's put it over here on the left, my sum is 0. I don't know anything yet. When I read this digit 1, I take the sum I have, I multiply by 10, and I add 1, so now my sum is 1. Then, let's change colors. When I read the digit 2, I take my sum, I multiply by 10, and I add 2, which gives me 12. When I see the digit 3, I take what I've got, I multiply by 10, I add 3 to it, and I get 123. Then I try to read a digit after that, and let's say I read a space here. I read a space after that. That's not a digit. I'm done. The sum is 123. 123 goes into I. So that's basically how Cn works. What we're going to do to turn a string into a number is the same approach. We're going to go through them one at a time. We're going to take our running total, multiply by some number, add the ASCII value of the next letter, and move along. So here we've got a string. We read TOM space M. Ooh, this looks like maybe a get line, or maybe it's already in a string object. I've already got it in a string object. I want to turn my string object into an integer. So I look at each letter. Remember, string objects. If I've got string S, I'm allowed to say things like S square brackets I to look at individual letters within the string. So what we do is we make a running total. I have a running total of 0. When I see the T, I take 0 times, let's say 10. 0 times 10 plus 84 is 84. When I see the letter O, I take the 84 I've got, multiply by 10, and add the ASCII value of capital O is 79. When I see the letter M, I take what I've got. This is my running total. I take my running total, multiply by 10, add the value of the M, which is 77, and we just keep doing this. We multiply our running total by some value, add the ASCII value of the next letter, that's our new sum. And when we're done with the string, whatever is in our sum is our final integer, hash integer. Shuffling the characters will usually change the result. So all of our examples before, spot and post and pots and stop, all of those would produce different integers. Now, it says here base 10 is used for illustration only. We should use primes, so if I was to say multiply these, if I was doing capital letters, I might multiply by, how many capital letters are there? 26. 27 is not a prime. I could multiply by 29. 29 would be a little bit better value. It's prime. It's bigger than the number of uppercase letters. What if it was upper and lowercase? Well, that's 26 plus 26 is 52. Is 53 prime? Maybe. If I multiply by something smaller than the number of primes, then I don't move the letters apart. If I just multiply by 1 or multiply by 2, I produce things that are easier to predict. Now we're going to come back to this topic at the end of the semester. Because of how the days in the semester worked out, we didn't actually do the strings and sequences lecture. If we'd done strings and sequences, we'd look at an actual implementation of this, all the code for it written out, and how to do this, how to do some other cool things with this. It turns out we're not actually going to use primes, but we're going to get primes in the equation in another way. Okay, so let's look at compression. So once we've got our hashed integer, one way to turn that into the range 0 to n would be, 0 to m. To turn it into the range 0 to m would be to do modulo m, remainder upon division by m. And that works just fine. Now, if m is prime, this works great. What if I can't control m? What if my hash table grows kind of like a vector does? It grows by doubling. If it grows by doubling, even if I start out at a prime, it's not going to stay there for very long. First time I grow the hash table, I've got 2 times a prime, and then I'll have 4 times a prime and 8 times a prime, and my primes are gone. So what about if I get some primes in there some way? All right, if I pick 2 primes, A and B, I pick those up front because I can't control M. So I pick A and B, and what I do is I take my hashed integer, whatever my translation function does, that gives me a hashed integer. I take my hashed integer times the prime A, and I add the prime B, and then I take modulo M. This will produce a little bit less collisions. It will not eliminate it. It can't eliminate them. But it might produce a little bit better, a little bit less collisions for a bit more complex hashing function, because now my compression takes longer to do. Now, for this to work, A modulo M must not be equal to 0. Well, as long as A is a prime and M is not a prime, the only way that a prime modulo M could be 0 is if M is equal to A. If we make sure M is never a prime, that it grows by doubling and starts out at something that's not a prime, we're fine. This will never happen. We'll never have A modulo M being equal to 0, which would produce a lot of collisions. Everybody would be at index B. Or I shouldn't say everybody. Anytime we got a duplicate. Or no, I guess that would be. Yeah, everybody would be at index B. Okay, so that's one way we could improve the compression a little bit. Generally, it turns out we don't tend to do this. It reduces collisions a little bit, but really we're better off with a good hash function. And one of the things we're going to be having you doing for an upcoming lab is we're going to give you a hash table that's mostly done. We're going to give you a hash function. You're going to use the simple modulo the table size. You're not going to care about primes. Just going to do whatever the hash function says, modulo the table size, that's where you put it. And so we're going to give you a hash table that's mostly done, and you're going to have to finish it by implementing a couple of functions. Now, let's assume we don't have collisions. That's what we'd like to have. So if we had perfect hashing, if everything always hashed to a new index, then what would be our cost of insertion? What would be our cost of search and our cost of removal? So if we had perfect hashing, if we never got a collision, if I always go to insert and there's an empty location there, it's O of 1 for all of these. Excuse me just a second. I have to cough and I don't want it being really loud. Okay, so if everything went into its own location, it would be perfect hashing. We'd get O of 1. Generally, we don't live in a perfect world. There is actually a way to do perfect hashing. There's an algorithm for it. But to do perfect hashing, you must know the keys up front. If you know the keys up front, and there's a fixed number of keys, you can make a hash function that will produce a hash table that is perfectly hashed. And the table is going to have to be bigger than the number of keys. And this algorithm is really complex. It takes a long time to run because the goal of this algorithm is to produce a function that says, take this letter, multiply by that, take this letter, multiply by that, etc. Now, you've actually been using hash tables the whole time you've been taking 281. In fact, you use them in 280, and you use them in 183 or Engine 101, whichever you took. The compiler uses hash tables. When the compiler is going through your code, how does it know when you say x equals 0, how does the compiler know that's valid? One thing it has to do is it has to say, hey, is x something I know about? And if so, is it valid to assign 0 to it? But the first part, the is x something I know about, is going to be done via hashing. So what the compiler does is it maintains a table, a hash table of user-defined identifiers. So when I say something like int x, first of all it has to say, do I know what int is? Do I already know what x is? Because if I already know what x is, I can't redefine it. Oh look, I know what int is. I don't know what x is, therefore this is a valid line of code. Then later on, when I say x equals 0, it takes x, it hashes it, it goes to the user symbol table and says, hey, is x in there? It is. Oh, okay. And then there's some code that says, is this assignment valid for the type of that variable? So we look up the variable, we find out that it does exist, we find out its type, and then we can determine that that is a valid assignment. Now, the compiler also does perfect hashing. How could it do perfect hashing? What could we perfect hash? Well, we can't perfect hash things like x because we can't predict all of the variable names and class names and structure names and function names, etc. All of the names that users could come up with, there's no fixed upper limit to those, so we can't perfect hash variable names. What could we perfect hash? What does the compiler have to process in your code that at some point in time was fixed and is fixed for this whole version of the compiler? There is in fact an example of it on the screen right now. The word int. The word int is a reserved word of the language. The reserved words are fixed for a certain version of C++, and so the compiler maker can say, hey, we know all the reserved words for this version of C++. They haven't added any since the last version, so we've already got our perfect hash function that we ran the code last time. It might take hours or even days to generate a perfect hash for like 50 reserved words. If the people that control the language decide we need a new keyword, then the compiler people have to rerun the code to produce a new perfect hash function. So really, when the compiler is reading your code, when it sees the word int, it says, let's perfect hash that. Do I know what int is? Yes, I do. It's a reserved word, and that happens really quickly. Then we say, what about x? We first try to perfect hash it, because that's faster than the number of user-defined identifiers grows. There's lots of functions and classes and variable names, etc. in a big program. So we first try to perfect hash it. We find x does not perfect hash into our reserved words table. So then we try the normal hash into the user-defined symbols table. Okay, so what about that idea of we can't sort a hash table? Well, the hash table, our really simple hash function here, starts out looking like it's alphabetical order. Apple, banana, lemon, mango, but then grape is not in alphabetical order. Even though we used a really simple hash function, the letter minus a, because we didn't make it as big as the number of letters, we got an ordering that isn't alphabetical order. If we had collisions, if I added apricot to this, maybe apricot would end up here, which is after the B's. It's not in alphabetical order. If I take this hash table behind the scenes and sort it, it no longer works as a hash table because grape and pear aren't at the index they're supposed to be in. Lemon and mango aren't where they're supposed to be. So if I were to sort it, it would destroy its functionality as a hash table. If I look through it from top to bottom, if I iterate through it, if I say, hey, unordered map, I would like to hash through the things in it. Or sorry, not hash, iterate. Hey, unordered map, I would like to iterate through the things in the underlying data structure. It would say, okay, well, you start here. I give you an iterator. You plus plus it, it moves here. You plus plus it, it moves here because there's nothing at index 2. The iterator knows that. The iterator moves forward to the next thing with data. So if we were printing these out, we'd print out apple, banana, lemon, mango, grape. Well, that's not alphabetical order. So this is why hash tables can't be sorted, because internally they are in hash table order. They're in hash function order. The hash function determines the ordering. If we had a different hash function, a little more complex than this, say one that took the letters and multiplied by a value and then added the next letter's number, etc., we would get a different ordering. It would be even less human readable. And we're going to see an example of that later today. So hashing. We wanted to get efficient insertion, search, and removal. We want these to be O of 1 on average, and we're willing to give up other things. We're willing to give up those other things to get that O of 1 average case. So in the STL unordered set, unordered map, unordered multiset, unordered multimap, these are all based on hash tables. And these have only been around since C++11, which was around 2011. And the people that control the STL is a committee, is a group that controls the STL, resisted adding hash tables for years. The community kept saying, we want hash tables, please give us hash tables. And they kept saying no, 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 and they finally said yes. And so they produced this implementation, unordered set, unordered map, etc. The reason they resisted adding hash tables for years is it's hard to make a hash table that is efficient all the time. It's easy to have collisions, and it's also a big trade-off on features. If I want more features, I have to give up some of my efficiency. And so they produced a version that is very heavy on features and is not terrible efficiency, but it could be better. If you, for instance, go to work at Google, Google has their own GTL, the Google Template Library. Google Template Library has, last I knew, since I don't work for them, last I knew, 3 extra implementations of hash tables, each version of which is willing to give up 1 or 2 features in order to get an increase in efficiency, an increase in speed. And so depending on what features you need, you pick the right version for you. So this is what the STL uses. We are going to avoid talking about the multi-versions. The multi-versions allow duplicate keys, actually meaning in a set you would just have duplicate keys, like you would have 2 5s. In an unordered multi-set, you could have 2 copies of the key 5. In an unordered multi-map, you could say, hey, 5 is associated with 2 different fruits. 5 is associated with apple, 5 is associated with banana. So the reason we avoid using those is 2 reasons. One, the syntax is a little bit more cryptic than the unordered map version. And the second is that if we want the behavior to be deterministic, there's a slight problem. With unordered multi-map, when you have duplicate keys, so I've got like 5 maps to apple and 5 maps to banana. If I use unordered multi-map and I say, hey, let's look up the key 5 and let's iterate over all the values associated with 5. On one platform, they get printed in this order. And if I change Mac to PC, they get printed in the opposite order. And if I go to the autograder, then that would be bad. Because depending on which platform you're on, you've got to write the code differently. So we don't want to deal with having to write code that way. So instead, if you read the project spec, we suggest when you need this behavior of a certain key has multiple values associated with it, what we do instead is we make an unordered map with whatever type of key we wanted, comma, vector of values. And that way, I say, hey, this key is associated with this vector, push back. I control the order. It always goes at the end. And I know if I add apple and then I add banana to the end of the vector, if I loop through them from beginning to end, they'll always be apple, banana. They will always be in the order that I pushed them back to the vector. Now, the compiler's using a hash for identifiers. We already talked about that one. Database indices, we have a completely different project 3, which you're not seeing, which is called SillyQL. And so SillyQL is a simplified version of SQL, or it's pronounced SQL. Is one of the most common database languages. So SQL, you can create a table, you can create an index, and those indices, this is a disk-based data structure. For real SQL, it's a disk-based data structure, but it does something like hash tables, just on disk instead of in memory. Now we're going to look at 2 sample programs here. One I've just got in the slides, the other I've got Visual Studio ready to go. So I've got here an example of, I want to keep track of the being able to look up a month and being able to see the number of days associated with it. So we've got includes of IOStream strings, since we're putting strings in the hash table, unordered map, and we make an unordered map. This is the key type, and this is the value associated with that key. Now, when I want things to be added to my hash table, the simplest way to do it is square brackets. So because unordered map is a class, it has overloaded operator square brackets. Operator square brackets has one restriction. Square brackets operator is only allowed to have one parameter. But there's no restrictions on type. So if we make it a string object, we can use double quotes because string objects have a convert constructor from char pointer into a string object. And so these get implicitly turned into string objects, and then the STL provides a hash function for strings. So when you're working on project 3, you don't need to write a hash function for strings. We go through it in the lecture to know how it could be done, but you don't have to do it yourself. You want to use the STL one. So we've got all of these get inserted because square brackets causes it to exist. And we'll look at what side effect that has in a minute. So I've just got a bunch of lines of code here to add them all in. And then on the next slide, we're going to have the user type in a month. And we're going to print out how many days are in that month. So we have them type a month name, and then we've got here the wrong way. We'll go back in a minute and see what happens with that. And we got the right way. So the right way is to say, hey, months, unordered map, call your .find member function, not find the STL. There is a standard : find that does a linear search. That's not what we're using here. We're doing the member function find is doing a hash table lookup. It says, find me this month in your hash table. It returns an iterator. So I used auto here because I didn't want to type the whole name. The whole name would be unordered _ map, angle brackets, string comma int, : iterator. Auto's a much easier way to get at that. So I say, hey, call months.find with this month. It returns something, and compiler figure out the type for me. I've got an iterator. It's important to know this is the place where you want to use pairs. Project 1, Project 2 were not the places to use pairs. Here we're using pairs because we have to, because the .find member function returns an iterator. The iterator points to a pair. That pair is always has first and second. These pairs are the key and the value. So when we get an iterator, the first thing we do with this iterator is check if it's valid. If the iterator is equal to the hash table .end, remember our sense. End is exclusive. It is not included in the search. So because end is exclusive, if the iterator is equal to end, that means it's not in there. If it's not in there, we print out an error message. We say that month is not found. Else, if it is a valid iterator, I'm going to print out the name of the month, the key, and the value associated with it, the number of days. I didn't have to use the iterator here. I could have said month. I didn't do month there because I wanted you to see that that's where it is. It's in it first. And I could have over here, I could have said months, square bracket month. Now I didn't do that for two reasons. One is that I wanted you to see that that second is the key. And I started to say out loud, I started to say .second. Here it's arrow second because we have an iterator. The iterator refers to the structure, so we need the arrow. So one reason is I wanted you to see that it second is the value. The other is using the iterator is more efficient. Using the square brackets has to go repeat the process of finding it, and that would be a waste of time. Once I've already found it, let's use the iterator and refer to it. Now let's look back at the wrong way to do it. The wrong way to do it is to go straight to the square brackets operator. Now the square brackets was great when I wanted to add to the hash table. The problem is here, before the cout even finishes, months, square bracket month, must return a value. If it doesn't exist, it must exist. It gets created in the hash table with the value 0. Here's something subtle. Remember when we did operator square brackets for our array class, and we wrote our own operator square brackets, and we wrote two versions. We wrote a const version and we wrote a non-const version. Hash tables do not have a const version because if the key doesn't exist, it gets created. So hash tables have only one version of operator square brackets, a non-const version that returns not an integer, it returns a reference, just like our non-const operator square brackets did earlier. So back here, what's really happening is as soon as we say months square bracket January, my hash table months, which used to be an empty hash table, now has an entry in it for January with the value 0 associated with it. It must exist before the square brackets even finishes. Then the square brackets returns a reference to that. Because we have a reference, we can assign the value 31 to it. So square bracketing something causes it to exist. So when we want it to exist, we go straight to the square brackets. I want June to exist, put it in there. But when I don't want it to exist, if it doesn't already, I use find. And this is critical for project 3. If some instructor would have, I don't know, written a test case that looks like this. C, junk 1. Keyword search, junk 2. Up to category search, junk. Keyword search. If someone were to do that with a very small log, if you use square brackets, you've just created 1 million entries in your category and keyword hash tables. If you go to square brackets, you're going to go over memory and probably over time also, because you're going to keep growing the hash table when it doesn't need to grow. So this is another reason why we want to use find. So there are places in Project 3 where you want to use square brackets. You want it to exist. And there's places in Project 3 where you want to use find to see if it does exist and look it up. Okay, next program I'm going to show you. There's going to be a very odd looking display here for a second because I'm going to switch my broadcasting software over to my desktop. And when I do that, it's going to, for a moment, have an infinite recursion of included images. Okay, so we're going to go to the desktop, and we're going to go over to Visual Studio here. Okay, so here's a program called Word Count Demo. It's on the Canvas sample code folder, Word Count Demo. So there's just one file in there, this CPP file. So let's make this a little bit bigger. Let's look at what's in this CPP file. Actually, let's just run it and see what it does. Okay, let's run this program, and it says, enter a file name. Well, I know one file name. I know wordcount.cpp. And what it does is it gives me the 10 most commonly used words in that file. It processes the file. It counts the number of occurrences of each word. Let's move that up a little bit, like include. 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8 include statements in here. The word the probably gets used a bunch in comments. I've probably got a variable named I. Word, oh yeah, there's word appears in comments and word appears as a variable name. I've got an integer I. 2 is probably in a bunch of, 2 and A are probably in a bunch of comments. If, while appear in code, etc. All right, so let's look at what this program does to accomplish this. Okay, we've got a how many words to display. We've got another using, for we'll come back to that one. Count sort, we'll come back to that. Cleanup word, let's go to main. Let's go to main here. Okay, so I've got in main, I've got a map. A map, wait a minute, I thought we were talking about unordered maps. Okay, fine, let's change this. The reason that it's there is because when I demonstrate this, I look at using different versions of this. So let's just run this. Oh, I'm going to do something cool. Let's watch this. Okay, so there's our output. I'm going to change the code. So we're going to make this unordered map, and I'm going to change it to unordered map down here. And we're going to compile this, and we're going to rerun it. Oh, shoot it. Okay, looks like it closed on me. Okay. Sorry, it closed on me and then I closed it. We get a slightly different order here. Still the same counts, but the words are in a different order. That's because we switched from map to unordered map. And I'm sorry it was in the map state. It's just that last time I demonstrated this, last semester, I kept it in my compiler, and for that class I changed from unordered to map to show that it worked. Okay, so we've got an unordered map, a hash table from strings to integers. That's my counts. That's how many times each word occurs. I've got a string for a file name and a word. I've got an input file, blah, blah. So I read a file name. Oh, look at this, do while loop. So I use a do while loop. Also very important for the project. 3, do while loop for reading commands. Why? Because I know I've got to go through the loop at least once. So the do while loop is like a while loop, except the while's at the bottom. Because the while's at the bottom, the body of the loop is guaranteed to run at least once. Great way to do the command processing for Project 3 Logman. So when we're doing Logman, we're going to process the input using this syntax. So I get a file and I keep trying to open the file name until it succeeds. Then it says, while you can read a word from the file. While you can read a word from the file, we're going to call cleanup. We'll look at that in a minute. If cleanup leaves anything, then we're going to do ++ count subword. So what's the first word in the file? Let's look at the top, //. // goes into cleanup, and cleanup, it says clean up a word by converting it to lowercase and removing all punctuation. Well, it does that by checking, is this thing punctuation or not? Punctuation is things that are not alphanumeric, basically. So alphanumeric would be letters and numbers. Punctuation would be things like semicolon, period, hyphen, etc. So it says, if this is punctuation, erase this letter and go back through the loop. Otherwise, replace this letter or digit with a lowercase version of itself. Converting a digit to lowercase doesn't change anything. Lowercase of 0 is still 0. So we replace it with the lowercase version of itself and we move on to the next letter. And it says we're done if we ever we try to go off the end. So the very first word, // all the punctuation gets removed and there's no word remaining. So our while loop goes back through, reads another word. It reads the word example. It cleans it up by converting it to lowercase. So we get lowercase example. But then we say, wait a minute, my unordered map has no words in it right now. As soon as we do this, example exists. It exists and the integer gets initialized to 0. Next time, I'm going to show you how that happens behind the scenes. We're going to look at a simple implementation of a hash table, and a little simpler than the one you're going to do in lab, and we're going to look at how that gets a 0 there. So as soon as we look up square brackets the word example, it exists with a count of 0, and then the plus plus can happen because the square brackets operator returns a reference to 0, plus plus changes the count of example to 1. And then we just keep going. Keep reading through this, keep going through the read loop, clean up a word. If there's any characters left, increment its count. And the hash table, the unordered map, takes care of all the data. It grows as necessary, takes care of all that stuff. So then when we're done, it says if you iterate over the unordered map, each word is in apparently random order. It's because they are in hash order. They are in string hash function order is what order they're in. Now we can actually do this. We can set a breakpoint there and say, hey, let's run this with the debugger. So we stop here. I'm going to have to go out of my full screen view to get, oh, actually I don't have to, counts. So we open up the variable counts and look at what's in it. It says right now it's size 49. It's got a hash function. It's got some other stuff. And it's got, here's the things in the hash table, case. So this is the key on the left. At least this is how Visual Studio displays it. The key case is associated with this pair. Case occurs once. Pair occurs once. Map occurs 3 times. Fstream occurs once, etc. These are not in the order they appeared in the file. They're not in alphabetical order. They are in hash function order. They are not in count order. I want the most common words. And see how it grows a little bit when I scroll through here to get longer ones. I want count order. I can't do that. So what I'm going to do is I want to produce these in their count order. And the only way to produce them in count order is to copy it. So what I did here, I've got a one way that's in, and I've got a couple ways commented out. It says, take my sortable vector, resize it to whatever counts.size is. Counts size is 49. So it says, make my vector size 49, then copy everything from counts begin and counts end, which remember is an inclusive exclusive range. Put it here, put it at the beginning of the sortable vector, and then sort the vector. So now we got to go look back at some of the things we skipped over. So my vector is a vector of word count pairs. Now let's look up to see how we did that. So word count pair is defined by using. This is considered the modern way of doing new types. That is really just a wrapper around an old type. So we say using new type name. I'm creating the name of a new type here. Using word count pair equals pair of string comma int. So basically this is saying from now on, whenever you see word count pair, it means this. So I create a functor. I'm going to need a functor to sort. I need to sort these word count pairs descending order by their count. So I've got a functor. I overload operator parentheses. I accept 2 word count pairs by reference. Const reference, const here. Can you get away without the consts? Sometimes. Sometimes yes, sometimes no. Sometimes it'll compile, sometimes it won't. It'll always compile if the consts are in here. So I've got my const, to const reference, const member function, promises not to change its member variables. That's easy, it's got no member variables. And then I base my return value on second. Left second is greater than right second. So if my parameters are left and right, and I use greater than, it produces a descending sort based on second. Second is the integer, which is the count. Okay, so back down here, I say, let's sort. Sortable.begin and end, count sort parentheses. I didn't do this lecture. I'm hoping Professor Darden mentioned this. What is this? This is an anonymous variable. So count sort, remember, is a type. It's a functor that we defined. Count sort parentheses looks like a constructor call. It's the shorthand for what's called an anonymous variable. This is a variable with no name. If I had done it in 2 steps, if I had said like count sort space sorting functor, and then here I had said sort blah blah sorting functor, that's a variable with a name. I said count sort space sorting functor, that creates a variable with a name. This creates a variable without a name, an anonymous variable. So I sort the whole vector, and then I want to display the most common pairs. This is something you probably encountered in Project 2A stats mode. You had to figure out the minimum number of things that you could do. So if I had a smaller file, maybe there's only 5 words. I can't display the 10 I would like if there's only 5 words in the vector. So I get the minimum number, and then we print out those entries in the sorted vector. So that gives us the sorted order descending by the count, because that's what count sort functor does. All right, I'm going to stop the debugger there. So that's what this one does. And if we, let's go back, let's just undo those changes and go back to map instead of unordered map. Let's compile this, and we're going to run it, and we're going to stop it with the debugger again. Okay. It didn't switch windows automatically. Okay. Okay, so here I've got counts. Counts is size 48. I guess I misread it before. Okay, now here it says entry 0 has 4 associated with it. So the display is slightly different. It doesn't display the pairs the same way on the right. But here they are in, it's not alphabetical order because there's numbers in here. There's a name for this. It's called lexicographic order. It means basically the whole ASCII table. So if you look at the ASCII table, the digits come before the lowercase letters in the ASCII table. So 0 comes before 1, 1 comes before 10, A comes before algorithm because A is a shorter string, and they both start with the same letter. So it turns out lots of things in this program start with AL. Algorithm, all along, alphabetic, alphabetically. So this is basically the map order. The map order behind the scenes, we can't see it. It's a balanced binary search tree. But the Visual Studio lets us look at it as if it was a table. And it lets us look at it in the order that if we iterated over it, it would iterate in this order. So now it's kind of interesting if we step over that and we step over that. If we look at counts right now, counts is in the order. We could have done this last time with the hash table. It's in the order that they were in the map. It's in alphabetical order, but we want it in order by the strings. So, whoops, I'm looking at counts. We should be looking at sortable. Sortable in the vector looks a little bit different. So yeah, here we go. So index 0, 0, 4, index 1, 1, 1, etc. So they got into the sortable vector in the same order. And then after we're done sorting, and we could have looked at this before, after we're done sorting, sortable is now in descending order by the count. Okay, I'm just going to go back to my code. I'm going to redo those changes for unordered just so that next semester it's in a good state, ready to go. Okay, now we're going to have our cryptic screen. Let's go back to my next lecture. Okay, there we are. Okay, so we're back to our slides. So what else do we have in here? We got a few more slides. Is major uses of hash tables. So if we're talking unordered sets or sets, unordered sets would be a hash table, set would be the balanced binary search tree. Cool things like checking for set membership, getting rid of duplicates, finding unique elements. There's even things we can do like, hey, let's say I told you I'm going to show you integers. I'm going to show you integers, one after another, and you have to tell me if any two of them sum to 0. If you didn't do anything, you would have to basically keep a vector of integers. So I'd keep like a 5, and then I'd say, okay, is 5's opposite? Is -5 in there? I'd do a linear search. Then I've got 5 and 3. Is -3 in there? Let's do a linear search. I see a 7. Is -7 in there? Let's do a linear search. No, it's not, so let's add 7. I see a -4. I say, is 4 in there? I do a linear search for 4, and it's not, so I add -4 to the vector. So if it was sorted, if it was unsorted, it would take O of n squared. If it was sorted, I could do a binary search. But to get the sorted order takes n log n. If I do this with a hash table, if I do what I just did, except I don't do a linear search, I do a hash table. I say, okay, I've seen a 5. Hash table, do you have a -5? No, add 5. Well, that lookup of -5 is average case O of 1. Adding 5 to the hash table is average case O of 1. I can now do this in O of n time with a hash table. Unordered vector would be n squared. Sorted vector would be n log n. Hash table, I can do it in O of n. Also, I can do key value storage, like counting things. We just counted strings and how many times they occurred. I can maintain sparse vectors if you've had linear algebra. We can do some other cool things. We can put a linked list in a hash table by making the key types and the value types the same. We could do, if we wanted to keep the index of a book, the index of a book, here would be a good place to use a map, because I want the map to be in alphabetical order I want the index to be in alphabetical order when I'm done. So here map would be a little bit better than unordered map, because when I'm done I don't have to copy over to a vector and sort. The key, the word, is the order that I want. So this would be actually a slightly better place to use a map than an unordered map. Composite data structures. You can actually do things with hash tables like maintain where things are in the world. We could do like longitude and latitude pairs and use hash functions to determine what is where. There's an example here of, hey, I need one key, but I've got 2 values that I want to hash, is doing something like the hash of key 1 plus some number times the hash of key 2. Is that good? And it's not really, because it's easy to predict them, where the collisions would be. It's easy to make up collisions. So if I know what P is, I can choose latitude and longitude that'll give me a duplicate key for the same two different latitudes and longitudes produce the same hash integer. So because it's easily predictable, that's kind of bad. If I can predict it, it's easy for them to occur naturally. So here's an example of a better hash combiner that uses XOR and left shift and right shift. And if you've seen 370, you know what they mean, but you don't know why this is good. I just hate telling you, no, that's not good, without giving you a way that's better. This is a better combiner, but it's a little bit cryptic on how it works. When shouldn't we use hash tables? So there's places where using a hash table is not the thing we want to do. There are some places where it would be better to do other things. In project 3, so now that you've found hash tables, you start feeling that, oh my gosh, hash tables are so cool, I should do everything with hash tables. And a lot of the time it's true, but it's not always true, and it's not always true in project 3. There are places in project 3 where you don't want to use a hash table. So one reason to not use a hash table is that hash tables do have a bit of memory overhead. And next lecture we're going to see why. If I put hash tables inside of hash tables, I get that memory overhead compounded. I also need to do the hash function on every access. So for instance, if my key was values in the range, let's say integers, in the range 0 to n, could I use a hash function? Sure. What would be better? A vector. A vector has a faster operator square brackets than a hash table. They could both use numbers in the range 0 to n as a key, but the vector would be better because it's faster. So sometimes, if we've got a small number of keys, that's easy. That was our birthday problem. If I have data that's never going to change and I could do binary searches on that data, that might be better than a hash table. This idea is going to come into project 3. This idea, project 3. So these are important things to consider. Where is this important? Where is this important in project 3? Now, also try to do what I showed you earlier, which is instead of looking up something 5 times in a row, if you look it up once with find and you've got the iterator, use the iterator 5 times. Instead of looking it up with square brackets 5 times, look it up once with the iterator and use it 5 times. Okay, and there's our summary slide. And next time, we're going to talk about the collisions on top of this and how to deal with collisions. So we're done for today, and I'm sure I'm going to see a lot of people in office hours later today. We're going to have probably lots of many-on-one questions where it's good to join the professors. Go to the office hours, join the Meet link that's up in the text description, and either ask questions or just listen to other people's questions about Project 3, and you'll get a lot of help out of that. See you later. I'm going to go log off and eat some lunch.